Okay, welcome everybody. So in this video, we are going to prove the following claim that for any m by n matrix A, the null space of that matrix is going to be a subspace of Rn, which is its domain. So recall in the previous video, we looked at this matrix A, and we were able to find the null space of A, and we represented this as the span of these three vectors. And we saw previously that any spanning set of vectors, by definition, is a subspace of the vector space from which those vectors live. So in this case, these vectors are all in R5. R5 is the domain of this matrix. And so this null space of A is a subspace of R5. So here we're trying to prove this in general, that this is true for any matrix A. So let's take a look at how this proof might look. So if we want to show that the null space of a matrix is a subspace of its domain, then we need to prove three things: that this space contains the zero vector, that the null space is closed under addition, and the null space is closed under scalar multiplication. So for the first property, why is the zero vector going to be contained in the null space of any matrix? Well, that's because for any matrix A, we know that the zero vector is a trivial solution to the homogeneous equation AX equals 0. So therefore, no matter what the matrix A is, if we take the matrix A and we multiply that by the zero vector, we are certainly going to get the zero vector on the right side of the equation. So we have that the zero vector, and here we mean the zero vector in Rn, is in the null space of matrix A. So that satisfies the first condition. Secondly, we would want to show that if we take any two vectors, u and v, that are in the null space of matrix A, that the sum of those two vectors, u plus v, also should be in the null space of A. So let's see what happens if I multiply matrix A by the sum u plus v. Well, we know that we have this nice property of matrix vector multiplication, that it's linear. So A times u plus v is equal to A times u plus A times v. And since u and v are assumed to be in the null space of A, by definition, when I take A and multiply by u and multiply v, we're going to get the zero vectors. So on the right side, we get 0 plus 0, which gives us the zero vector. Therefore, u plus v is also in the null space of A. So we see that the null space of A is closed under vector addition. And thirdly, for scalar multiplication, if I take some vector u in the null space of A, and let's let C denote any arbitrary scalar, then we know also as a property of matrix vector addition that if I take matrix A and multiply by C, I multiply matrix A times the vector CU, that we can pull out that scalar multiple C in front of the product. So I can first take A and multiply U, and then multiply by the scalar C. And since u is in the null space of A, we know that AU is going to give us 0. So regardless of what scalar C is, any scalar times the zero vector would give us the zero vector. So therefore, multiplying matrix A times the vector CU gives us the zero vector. That means that CU also has to be in the null space of matrix A. So therefore, this is closed under scalar multiplication, and we've just proven that the null space of a matrix A satisfies all three of the required conditions for it to be a subspace of the domain Rn, which is equal to the number of columns in that matrix.